Okay, so I'm going to introduce myself tonight. So I'm going to fill in the second slot for tonight with this thing that I've called product development leverage. Really, I was talking at the break. It's a bit of a hobby horse of mine, really, that engineering teams in general, as we've already, Jason talked about in the first half of tonight's meetup, that engineering teams very easily get disconnected from the value that they're creating or the reason that they're creating features, especially in large organizations. And I think they also get disconnected just in what the features are even trying to do, or some of the subtle design decisions that they could take. And some of that stuff is helped enormously by a more iterative sort of set of delivery methods like an agile team would do, but it still doesn't go all the way. And it's a little hobby horse of mine. I think that engineers could be far more influential and deliver better solutions or more commercially better outcomes by probably doing what they're already doing now, but by equipping themselves with a set of tools, often thinking tools, I think, to help them make good decisions. And hopefully tonight, we're going to drill into some of that stuff. So I'll whiz through the introduction because you know me already. We're going to talk about some definitions and then a kind of mental model, a way of thinking about some of these design decisions, and some real-world examples at the end, which will hopefully might elicit some discussion at the end as well. So, you know me, NewRedo is a business that we started in 2011, building software for all sorts of people. So we build all kinds of things. And some of what we're going to talk about tonight has come out of that experience, really, because at the end of the day, we have to keep the lights on. This is me back in 1988. So I think this is it wasn't my first job, actually. I think this was my second job with what am I holding there? It's a bank of Hitachi replica IBM tape drives behind me. I think it's an IBM 2420 or something tape drive that held about, I think it was about 100 meg of data or something like that. So I've done all sorts of things for a long time now, and built things in all sorts of different ways. And some of my experience of what's worked and what's not has sort of rubbed off on me over time and influenced the way that we do things at NewRedo. I've got 2 kids and a barking dog as well. I'm just showing this folder because this has all kind of influenced the fact that it's important to we're building software in a commercial context. We have to regularly raise invoices to feed this lot, and at the same time, as Jason pointed out, we've got to solve customers' problems and deliver value to them. Otherwise, they don't come back. So tonight's little discussion here really is around trying to get some mental models in place, and hopefully it will allow you to think about what you do in a slightly different way, or perhaps make some of the decisions that you make in a slightly different way. If you've got any questions, stop me as we go through, or we will definitely have time for questions at the end as well. So definitions. There's this term leverage. This is a screenshot straight from Google Dictionary. We all know what a lever is in terms of a piece of a long, thin rod of some description that affects some mechanical advantage. It turns a low but long force into something that can apply a high level of force. And that metaphor has been used by the financial industry. And this is the kind of the piece of this definition that's most important for tonight. So back in 2008, we heard about it a lot when the banking crisis was just starting. So the use of borrowed capital for an investment expecting the profits made to be greater than the interest payable. So the financial industry uses this all the time to borrow money and invest in something where they're expecting some return to exceed the interest that will be paid on that initial investment or the money that was originally borrowed. And that's exactly the same metaphor that Ward Cunningham used when he first coined this technical debt phrase. So everyone's heard of technical debt. Who's anybody in this room never whiled away hours and hours in the pub with their fellow developers talking about technical debt? So I know technical debt gets talked about in this meetup probably about every other month in some way, shape or form. And it's, you know, a source of much frustration, I think, to lots of engineers. But I think actually it's a tool for all of us to use in our toolbox, and thinking about it in the right way it empowers product development teams to be far more influential and to, you know, increase the value and influence of what they do. So technical debt is a concept in software development that reflects the implied cost of actual rework caused by choosing an easy solution now instead of using a better approach that would take longer. So it's exactly the same idea as exists in the financial sector. We want to do something which creates some value now, but is cheaper, so that we can get value back quicker and avoid a more costly implementation which might take longer and delay that returned value. Does that make sense? To kind of. Is that
exactly the same as hardening, or is there a difference?
As hardening. I suppose you might think of hardening as a bit, I suppose I'd think of that as a bit like paying back technical debt, I suppose. But you know, hardening, for me, hardening is everything doesn't have to be hardened. You don't always have to pay back technical debt. No, you know, that's one of the I suppose it's you know, it doesn't exist in the financial sector, in the financial industry in the same way, where you can borrow money but never pay it back. And therein lies the empowered nature of what we can talk about tonight. As engineers, we actually may, in certain circumstances, build something that is best left alone. So this is one of these quadrant diagrams from Martin Fowler's website. So Martin Fowler, well, many people have, Ward Cunningham originally coined that phrase, technical debt, but Martin Fowler's talked about it an awful lot as well. But this quadrant diagram really is a bit more about kind of being conscious when you're using technical debt or using it sort of thoughtfully. It doesn't really talk too much about the commercial context or the economic model surrounding it. So in this quadrant we've got on the vertical axis inadvertent technical debt, so doing stuff wrong by or let's say cutting corners by accident, or as against doing it deliberately, and on the horizontal axis being prudent about how you implement things, as against being reckless. So up in this top corner here, we must ship now and deal with the consequences. So a team knows very well that they're going to cut some corners, or they're going to implement something in perhaps a less costly way. Doesn't necessarily mean cutting corners, but there's some compromises made. But they're fully conscious of that, and they've made a conscious decision to do it because they want to get something out the door. And getting something out of the door allows that value in terms of feedback, or revenue, or new customers, or competitive advantage to come back early. Down here, this is about some design compromises were made, implementation compromises were made, and inadvertently some technical debt was made. This is often the case. This is where we sit a lot of the time when we've built something And in the process of building that, we've learned far more about the problem domain. And in the process of learning about the problem domain, we've realized actually we could have done things differently. We could have modeled things differently. We could have built the code differently. And at some point in time, if what we're working on matures, we may go back and change that. Who's not been in a situation like that where they've looked back and thought, I could have done that a bit differently? Happens all the time. It's the world we live in. Okay, on this side then, so the left-hand side of the slide here, this is all things where, this is the kind of the area that frustrates, I think, a lot of product development teams. So we don't have time for design. We know we're doing it, but we're just going to walk headlong into it and with our fingers crossed, and hopefully something's going to, it's going to be all right in the end. And I think this is perhaps the source of frustration for a lot of people. And then down in this corner here is like, I don't know, teams that have, they don't even know that they've implemented something wrongly. They don't know what they don't know. So that's the kind of the state of the union, as it certainly is on Martin Fowler's website, but that, I think there's some other layers to this that we can talk about tonight. So another little definition then, cost of delay. Are people familiar with cost of delay? Is it something that kind of, wasn't really mentioned much in the early years of Agile? Scrum doesn't really talk about cost of delay, even though some of the practices that it recommends certainly help with cost of delay. But so the cost of delay is a way of communicating the impact of time on the outcomes we hope to achieve. That's kind of a bit abstract. Or the cost of delay combines an understanding of value with how that value leaks away over time. So, so by not implementing something today, we're not getting the value from it today. The longer we don't do something, the more the value is slowly leaking away because the world is still turning. All sorts of things are changing. The commercial environment's changing. Competitive pressure is changing. Technology is changing. What customers want is changing. The longer we leave things, the kind of less we know about what we were trying to achieve. That makes sense? There's some other sort of layers to cost of delay as well. So any kind of cost of delay has some kind of profile. Every piece of functionality doesn't degrade in value in exactly the same way. Up in this top corner here, kind of a standard feature, let's say, this is often used. So a standard feature that we might implement as part of a solution which is perhaps saving some kind of cost for a business. The longer it's not in place, the more it's slowly costing us. So the sooner we get that built, the sooner it's going to help the bottom line. Down here, fixed date, style, needs. We may not. This is typically the kind of profile you might see from a piece of regulatory change. So something is needed to be implemented, by the autumn statement or something like that. So it may have little or no value up until that date because it's, we don't need to be compliant now, but in September, or is it September or October? When we do, all of a sudden, if it's not in place, it's going to be hugely costly to us. So, you can use that profile to help with scheduling. If we've got the capacity available, there's no point in doing it now. We can implement something with a standard profile and get the value out of it. But we definitely want to be starting to implement it in August or something, or whenever, when I leave enough time to be able to get it done. This term expedite is often used for things with a cost of delay like this, where something's happened, there's a crisis, we need to get something fixed now, we need something implemented. It could be something technically is broken, or it could be a competitor just launched something, but it's all hands to the pump. And then down here, this is often, this intangible kind of class profile is something that's often applied to things like engineering, housekeeping, where we know there will be some cost eventually if we don't move from MongoDB version whatever to a later version. We know there will be some cost. Perhaps it's not going to be supported, or there'll be some other issues. We don't quite know when that cost is going to kick in. So timing is a little bit more difficult to achieve, but we know if we don't do it in the long run, it'll definitely hurt us in some way, shape, or form. So all that stuff, you need to, hold this in your head and think about this as we move on a little bit. The other definition, cost of failure then. So cost of failure, or the cost of poor quality, COPQ is how it's often referred to in kind of manufacturing, lean nomenclature, are costs that would disappear if systems, processes, and products were perfect. So nothing's ever perfect. And sort of both poor quality and what is perfect is a little bit subjective as well, depending on the context we're kind of building things in, and that's something that's kind of something about what we're going to talk about in the next, as I just move on now. So clearly, something of poor quality and being perfect means something different in an air traffic control system where there's hundreds of people flying around in aeroplanes that might meet in the sky, to something that perhaps is, a social media website or something where the consequences of failure, some people would say anyway, maybe not quite as disastrous, immediately disastrous at least. So that's some definitions now. I just want to really move on now to another model. So this notion of high cost of delay against low cost of delay on the horizontal axis and high cost of failure and low cost of failure, this pendulum between, or this balance between the cost of failure and the cost of delay is really something that engineering teams can use to their advantage, and to help to provide the right kind of solutions, the right kind of analysis, depending on the context. So up in this top corner here, where we have high cost of delay, high cost of failure, sort of things that are absolutely must be done, and they absolutely are critical. So, probably your air traffic control, well, maybe your air traffic control system wouldn't fit in this, but, there's things, anything that goes wrong in this on this side of the slide tends to be really expensive. But we want to get this stuff out the door very quickly because the cost of delay profile is hurting us. Down in this quadrant here, it's required, but we are tolerant to some kind of failure. The failure isn't necessarily that costly. In this top left-hand corner, things perhaps less critically, it's less critical that they're delivered immediately. Perhaps not completely optional, but cost of delay has more leeway. But failure is still important. It still can be costly. And then down here, optional and fault tolerant. So here's a few kind of traits for the kinds of things that we typically see fitting here. So in this top right-hand corner, mature products in competitive markets. So competitive pressure is one of the things that tends to drive things into this top corner, because it's important to get features in the hands of customers. It's important because over time customers might leak, companies might lose their market share. Critical systems, or sort of desktop, probably should be better described as shrink-wrap software, things that where the cost of failure once things have been deployed is typically higher than might be with a kind of SaaS application. This is perhaps the area where perhaps most of us work most of the time, where the cost of delay is significant, but we know we can mitigate cost of failure with some tactics that we're going to talk about. So, startup MVPs, who's kind of involved in writing MVPs, minimum viable products. There's a kind of a buzzword that everybody uses now. And if you look at the kind of the government digital service guidelines, there's some fairly prescriptive kind of ideas about what an MVP might be. I think in the kind of the sphere of startups, it can be a lot more flexible than that. Often it might not necessarily be anything that is particularly working for customers, but it's certainly going to help some learning of some description. So it is important it's built quickly, because learning fast is one of the advantages that kind of startups have. Cost of failure, if a product fails when it doesn't have many customers, or a business is really small, then the consequences are far less. Once products start to mature, customers are relying on them, then the pendulum has started to swing. And kind of also experimental features. So even in a mature product, with an established feature set, it might be that there are differentiating features that some customers might want, other customers might not want. Where we're in a dilemma. There might be a sort of product management dilemma about how those features might be used, whether they're going to add value or confuse, make the product more complicated. Using tactics where things like feature switches might be appropriate that would allow certain features to be turned off or turned on for certain customers, and learn what's been used and what isn't used. Up in this corner here, so cost of failure is high, cost of delay is low. So these things they do need doing. They're not perhaps deathly urgent, but the cost of failure can be really high. So shrink wrap software used to be used to be something that was extremely costly to, releasing bugs into the wild was extremely costly for shrink wrap software, because of all sorts of not really hidden costs, but soon to be realised costs. Just the costs in the telephone ringing, the support, unanticipated support costs, building patches, deploying patches, potentially fixing corrupt data. And for really mature, really popular products, those often, reached huge quantities, huge amounts of money. And down here, low cost of delay, low cost of failure. These are all stuff that's on the bottom of the backlog. Luxury items, low value work. Probably, I don't know, you've got to question if you're down in this corner here building anything, perhaps you ought to question whether it's worth doing at all. So I've got some examples to talk a little bit about. I haven't really got an example of anything down here, just because, as I say, probably it's work that has little value, and if it fails, has few consequences. I'm sure we've all built things, but it's not the interesting piece. I was at Sage for a while, so I'm going to talk a little bit about the Sage and what went on there when this is going back a few years now, when everything was deployed on a DVD. And something about Race Best is something that we've been involved in as a startup business. And then a little story about Formula One, the Lotus Formula One team, some tactics that they use to, in a context which isn't software development, but where the cost of delay is extremely high. We're going to drill into each context a little bit. So the Sage, shrink wrap software then. Because of all those costs involved in deployment and distribution, really, it was always really important that things didn't escape into the wild, bugs didn't escape into the wild, and enormous amounts of money were spent on QA. In a similar way now, I'm sure that certain mature software as a service products now are in a similar position, just because once a feature set has reached a kind of certain maturity and the customer base is large enough, persistent failure will start to leak customers. But back in the days of shrink wrap software, if a bug was discovered once a release had gone out, then there was an enormous kind of panic swept across the development team because of the inherent cost and impact on the business that was going to ensue. My slides might be a little bit out here. So I'm just going to talk a little bit about Race Best now. So Race Best really fits into that kind of startup category. Race Best is something that we built back in about 2012 and launched it in 21 days. When we first launched it, it didn't have, I think it had one admin page and about 3 production pages. Now there's about 100,000 pages a month, 50,000 runners have entered, about 40,000 visitors a month. But it's a startup scenario, and the important point was to try to get the thing released as fast as possible in order to see if there was, what the customer need was, if there was going to be a customer reaction to it. And these are all kind of similar tests that get employed by lean startup style businesses in an attempt to kind of reduce that cost of delay and increase the speed of learning. So customer interviews, A/B tests. People heard of the Wizard of Oz style, Wizard of Oz test and concierge. So when we first released Race Best, there was quite a lot of Wizard of Oz going on in the background. There was absolutely minimal functionality. There was no real way to publish results. People emailed them in, and there was a bit of string pulling in the back to get the things live. Lots of actually even listing races in the first place were done on a very concierge kind of basis. People would fill a form in, and an email would come in, and somebody would ring them back and kind of walk them through the process of getting a new race live. But it was enabled the whole thing to be launched very quickly. Some of these other things, crowdfunding, Google AdWords, landing pages are all things that help just very quick and easy to implement. Has anybody ever seen, people familiar with Buffer? There's lots of Buffer posts about the early kind of landing pages that they built, and MVP prototypes and single feature MVPs that we're all sort of familiar with. So I'm just going to talk a little bit about, we did some work with the Lotus Formula One team a few years ago, and that was a kind of fascinating experience in a business that wasn't a software business, but was very similar to software, in so much as it was all about design. So, you know, most of the time in a business which is making stuff, in a manufacturing style business, the costs involved with design aren't quite so important because they're going to be amortized over producing thousands of, you know, whatever it is you're producing, widgets, toasters, or whatever it might be. But in a Formula One team, it's kind of similar to software in that the actual manufacturing production part of it is you know, everything's done on a very low volume basis. We're never making half a dozen parts of any part of the car before the design moves on and something evolves and there's a new iteration created, which is similar to kind of software in that it's all about design. The production part, the manufacturing part, I suppose you might see that as analogous to the kind of deployment, but it's a minimal part of the cost of the whole thing. It's a design race that's the important thing. Now, at the time, there was a guy called James Allison running the team. He was the technical director. And one of the problems that they'd encountered a couple of years before were the every season, when they finished the F1 season in August, they would typically, by that time, they'd have a new set of rules. And between August and Christmas, they would use that time to build a new chassis based on the new rules and the new design constraints that they knew they had. And at Christmas, they would then submit this chassis to the FIA for crash testing. So it needed to be crash tested before they could, for them to use that chassis for the following season. They would all go home for Christmas with their fingers crossed, and they would all hope that they would come back after Christmas with a chassis that had passed crash testing. And if it did pass crash testing, then they would, I've got a picture of crash testing here. If it did pass crash testing, they would be happy, and between the new year and the start of the F1 season in kind of Easter, April time, they could continue to develop the car and hopefully make it go faster and faster. However, if they didn't pass crash testing, they had a problem, because now it was the new year. They needed to spend time redesigning the chassis, resubmitting it for crash testing. Now that created all sorts of problems for them. The cost of delay was enormous, because now they would lose that development time. So this slide just shows so this is the normal timeline. They're building the chassis from August to Christmas. They go to crash testing. They come back after Christmas, and off they go with more development. And hopefully, at the first Grand Prix at Easter, you know, they're somewhere near the front of the grid. If the car fails crash testing at Christmas, they're back into rework now. They're back into rebuilding and resubmitted for crash test, and now they've lost all this development time here. So for them, this cost of delay was enormously important. And the previous year to the time we were there, this is exactly what happened, and it had a huge impact on how the rest of the season had unfolded for them. So what to do? They didn't know what to do. How could they sort of mitigate some of these risks? And this is not dissimilar to a software team, but you know, perhaps up against a competitor trying to release something, and it's or perhaps for some sort of regulatory reason, there's something which means that by missing a date or by failing at a certain point, it's going to be extremely costly. So what did they do? So the answer was an extremely costly one. But they were in an extremely costly situation. The answer was to kind of start to employ parallel development. So the parallel development is something that I think gets, you know, gets used by software teams, people like Google, Facebook, I'm sure, where they've got multiple versions of the application running at any one time. Because of the competitive pressure that they face, that's something that makes sense for them. In a Formula One situation, it absolutely made sense. The reason it made sense is because they could be absolutely certain they were going to start after Christmas with a clear run to Easter to develop the rest of the car. And what they would do, they would build 3 chassis. They would build a super light chassis. They would build a kind of slightly beefier medium weight chassis, and then a hugely sort of well-engineered heavy chassis. And a week before Christmas, they would submit this super light chassis with their fingers crossed. If that came back from the crash test passed, they knew they were golden. It was they had a super light car. They knew they were going to be fast. Everything was great. But even if it failed, they had another one up their sleeve. They hadn't necessarily lost time. So they would immediately submit the next one a week later or a couple of days later, knowing that almost certainly that was going to pass. But even if it did fail the second time, they had another one, a third one up their sleeve that they knew is absolutely no way it could fail. So instead of gambling on this development time, they were gambling on how light a chassis they could build, basically. So they'd switched. By investing in 3 chassis instead of 1, they'd switch the odds in their favour. And you know, kind of reduced one of their risks enormously. And to be honest, you know, it was one of the things which you know, was talked about a lot in the just across the business as a whole, because this kind of getting parts through the design pipeline and throwing away the bad ideas was the thing which really enabled them to be competitive. They even used to use a metric they called aero points, because it was between each Grand Prix, finding enough aero points to be able to develop the car and make it more slippery was the thing that enabled them to stay kind of where they were on the grid or go forward on the grid. And if they couldn't find those aero points, that would be the thing that would start to make them go back on the grid. Yeah, so these are all really, you know, it's thinking about that, the pendulum swinging between cost of delay and cost of failure, and the difference between, you know, early venture startup businesses where the cost of failure might be low, and as they slowly mature, the pendulum swinging towards cost of delay being higher. And you know, in some of these other situations and contexts where the competition is such that investment in things like parallel development can make sense. And that's kind of me done.